Okay, these are the questions we went over in class, but I want to go over them here for anyone that was absent. So we'll go over 1 and 2, and then you guys will be responsible for doing 3 and 4 on your own. Number 3 is just like number 1. Okay, we're doing the same steps. And number 4 is just like number 2. Okay, so if we look at number 1, when you're dealing with calorimetry, okay, it's important to know that your heat, remember Q is heat, your heat absorbed is equal to, but has the opposite sign of your heat released. Okay, so it's important whenever you're doing calorimetry or thermodynamics in general, you keep in mind what's absorbing heat and what is releasing heat. Okay, and this is all because of our conservation of energy, right? This is our practical. Energy can't be created or destroyed, which means it has to come from somewhere. So when we see that our water originally has 25 degrees Celsius, it's heated up to 34.6. That's because we've added a hot sample of nickel to the water. Okay, and we know that the temperature increase is going to mean that heat was absorbed by your water. Whenever you see calorimeter or calorimetry, you should always think Q equals MC delta T. That's your calorimetry equation. We're calculating heat. We can't measure directly heat, but we can measure temperature, we can measure mass, and we know that C, I'll write it up here, C is specific heat, and specific heat is based on, or it might be easier to remember, C is specific heat, and specific heat is specific to the type of material. Okay, specific heat is specific to the type of material. So when we're measuring our calorimetry problem, we have to figure out what we're trying to find, or what is our unknown in our problem. So what is the temperature of the nickel before it's dropped into the water? That means we're trying to find our initial temperature of the nickel. Okay, that means we need to use Q of the nickel is equal to the mass of the nickel, the specific heat of nickel, and the change in temperature, which is T final minus T initial of the nickel. If we look at our problem, we have a 30-gram sample of nickel, so we know that our mass is 30 grams. The specific heat of nickel is, specific heat in general is always going to be a value that you can look up. Okay, so if we look it up on the front of your packet, okay, on the front of your packet, the specific heat of nickel is 0.444. Okay, so the specific heat is 0.444, and the units are joules per gram degree Celsius. And then your final temperature is right here. Okay, the water is heated up to 34.6. Your final temperature in calorimetry problems, that's going to be for the nickel and for the water. Okay, and that's because of something called thermal equilibrium. Thermal equilibrium means that once you dump that hot sample of nickel into the water, the temperature of the nickel is going to go down and the temperature of the water is going to go up. They're going to reach some equilibrium or equal point. Everything wants to eventually reach thermal equilibrium. That's why if you leave, let's say, a cup of coffee out at room temperature, the coffee is eventually going to cool down to reach room temperature. Okay, it's going to achieve thermal equilibrium. Same thing when we did our calorimetry experiment in the lab. You heated up aluminum to 100 degrees Celsius. If you tried to dump that into your hand right away, you would burn your hand. However, we put it into the water bath, into the water in the coffee cup calorimeter first, and it immediately decreased in temperature. Okay, the water started around 20-25 degrees Celsius. It increased in temperature to around 27-30. So at that point, the water and the nickel both were around 27 to 30 degrees Celsius. So if you tried to, when you took the nickel out of the coffee cup calorimeter to dry it off, you could pour it into your hand without burning yourself because it had reached equilibrium, thermal equilibrium with the water. Okay, so this final temperature here is the final temperature for your water as well as the final temperature for your nickel sample. So 34.6 minus your initial, which is what we're looking for. We also need to know the heat of the nickel. We don't have that number because in our question, we're not given any information about heat. We don't see heat, and remember, heat is measured in joules. We don't have any information about joules in this question either, so we don't know this. So let's look. We do know that the energy released by the nickel is going to be the negative sign, or opposite sign of the energy absorbed. So if we look here, our water is increasing in temperature, which means our water is absorbing energy. Our nickel is releasing energy. So if we can find the heat of our water, then we, by default, know the heat of our nickel. So Q water is going to be equal to the mass of the water times the specific heat of water and the temperature, the final temperature, minus the initial temperature of the water. We have all of these variables in our question. So the mass of the water is 150 grams. Specific heat of water based on our reference packet. Water is liquid at room temperature, so 4.18 joule per gram degree Celsius. Our final temperature is 34.6, and our initial temperature is 25. So we can calculate the heat of the water to be 6,019.2, and our units, grams cancel grams, Celsius cancels Celsius, our units are joules, right? And we know this because our units for heat are joules. So we can use conservation of energy. Q water equals negative Q nickel to get negative 6,019.2 equal to 30 grams times 0.444 times 34.6 minus your T initial. What we're going to do is we're going to combine these two and then distribute. So when we do that, we get negative 6,019.2 joules is equal to 460.872 grams cancel out, so joules per degree Celsius, and 34.6 minus your initial temperature. Then we're going to distribute this 460 to both temperatures. We get negative 6,019.2 is equal to, this number 30 times 0.444 should be 13.32. When we distribute, then we get 460.872. Distribute here, minus 13.32 times your initial temperature. We're going to subtract 460 on both sides, so we end up with negative 6,480.072 is equal to negative 13.32 times your initial temperature, and our initial temperature is equal to 486.5 degrees Celsius. Okay. Using that, you can do the same exact process for number 3. So keep in mind what's absorbing heat, what's releasing heat, and use the heat of the water to solve for the initial temperature of your nickel. If we look at number 2, you have a 500 gram sample of water heated to 95 degrees Celsius. It's poured into 150 gram sample of solid nickel, originally at 10 degrees Celsius. So we have water and we have nickel. The water is being mixed with, so the water starts up here at 95 degrees. The nickel starts at 10 degrees Celsius, which is lower. They're going to reach thermal equilibrium somewhere in here. So that means the water is releasing heat and the nickel is absorbing heat. We want to know the final temperature of your nickel. So we're going to use Q nickel is equal to the mass of the nickel times the specific heat of nickel and the change in temperature. So we want the final, T final, minus T initial. The initial temperature of the nickel is 10 degrees. I'm skipping steps over here. Initial temperature of the nickel. Alright, so the mass of our nickel sample is 150 grams. Specific heat of nickel, find it from the front of our packet, 444. Our final is we don't know, minus our initial, which was our 10 degrees. We also don't know the Q, because again, in this question there's nothing about joules. Oops. There's no information about joules, so we still don't know the heat of the nickel, but we know that the nickel is absorbing heat, so it's going to be a positive number. Let's look at our water. Let's see if we can do the same. So we have Q water, W is water, is equal to the mass of your water times the specific heat of your water and the change in temperature, T final, minus T initial of your water. We know that the mass of your water is 500 grams. Specific heat of water is 4.18. The final temperature, okay, remember whenever you have final temperature is thermal equilibrium. So if we don't know the final temperature of the nickel, that means we also don't know the final temperature of your water. We do know the initial sample temperature of the water was 95 degrees Celsius. And we still don't know the heat of the water, but we do know that it's got a negative sign. So we have two variables in this equation and two variables in this equation. You can't solve an equation with only two variables, but you can set these equal to each other because we know that the heat absorbed is equal to the heat released. So we take this negative sign and bring it over here. We have negative 500 grams, 4.18. Right, this negative is going to distribute to everything, 4.18. Final temperature minus 95 degrees. Set that equal to positive 150 times 0.444. Final temperature minus 10. So the first thing we're going to do is combine these. So we do 500 times 4.18. We know that it's going to be negative, so negative 2090 temperature final minus 95 is equal to 150 times 0.444. We get 66.6 times your final temperature minus 10. We're going to distribute this on both sides. So negative 2090 times your final temperature is equal to positive, the negative times the negative is a positive, 198,550 equal to 66.6 times your final temperature minus 666. Now we just rearrange and solve for our final temperature. So we can add to both sides, and we can subtract, or add, I guess, 2090 TF, 2090 TF to both sides. So this is going to cancel, and this is going to cancel. You're going to end up with 199,216, oops, is equal to 2,156.6 times your final temperature. Divide, and you get your final temperature equal to 92.4 degrees Celsius. Okay. This one, same as number 4. Just keep in mind which thing is releasing energy, which thing is absorbing energy. That's how you'll know where your negative sign goes and where your positive sign goes.